To the OneClass channel. My name is Fejiro, and I'm an honors Bachelor of Science student working towards medical school. Tonight we'll be going over some commonly asked chemistry questions at both the high school and college levels. If you need some homework help or tutoring, check out the links in the description below. And with that, let's hop right into our session for today. So, let me just set things up and begin. So the first question is asking, how many quarts are in a gallon? So these type of questions, it's important to either memorize it depending on your professor or refer to the conversion sheet they gave you. And the goal here is to make sure that you're converting the right units. So we know what we have, which is a gallon, and we know what we want, which is quarts. Okay, so with that we can say 1 gallon times, and now here's where it gets interesting. To keep your units, you always want what you have in the denominator. So something gallons and at the top quarts. So now with that would equal something, and then the units will cancel out, leaving you with just quarts. But let's see what our handy dandy conversion sheet says about quarts and gallons. So for every gallon there's 4 quarts. Okay, pretty simple multiplication here. So with that, just getting ready with some other tools of mine, we're just gonna have this equal 4 quarts. So for your question of how many quarts are in the gallon, there are 4 quarts in 1 gallon. And seen here, that is correct. So let us move on to the next question. So number 2. This question is asking, what is an alkyl group? So I'm sure you can see a little bit of what it says down there, but an alkyl group is, if you think about it, is a chain of carbons and hydrogens attached to a main group. So these are all these types of functional groups. So an alkyl group counts as one of said functional groups. And there's many types of functional groups. There are carbonyls, carboxyls, benzene, phenyl groups. I'm just saying a bunch of things, but point being is, in an alkyl group, think of it as like the most basic you can get, because when you start talking about like an ester group or an ether group or something like that, those ones have specific types of different elements in them, like oxygen, but alkyl groups only focus on carbon and hydrogen chains. So it's kind of like an extra chain that sticks out. So let's say, for example, we had a benzene ring. Okay, and this stuck out of it. Okay, so because the benzene ring is our main group here, that is what we will base it off of. So like it'll end in a benzene. Okay, this here, this 1, 2, 3 carbon chain, that's C3H. It's gonna be, yeah, this is about C3H7. It would usually be C3H8, but then it's attached here, so that would be like the last part. But point being that this carbon group, because there's 3 carbons, this would actually be pro benzene, propanil benzene. And actually, if we actually search it up here, oh, I added too many parts. So propyl benzene. If you look at the picture, so propyl, not propanil. It's just important to also know where the so a 3-carbon ring, that's propane. So it's important to know where it drops off. So this ANE gets canceled out and replaced with a YL, which is what alkyl groups are. I'll give you another alkyl group after, just so we make sure that we get it on point. But the point being is that, as you see here, propylbenzene, exactly what I drew here. It's a benzene ring with propane group, propyl group sticking out of it. So let's say, for example, also if you're thinking about alkyl groups, I'm gonna say, I guess benzene is really the best one to work with because it's usually its own. It gets one of the highest priorities. So if we had a benzene, okay, and then we did this like that, right? So it goes back to your nomenclature. You always want to be naming, like, try to get things at the highest priority. So this will be the best for 1, 2, 3, 4, 5, 6, in my opinion. And then I'll circle 1, 2, 3, 4, and then this one has 3. So 4, so that's butane. So we can drop that off. So it'll be actually butyl. This butyl right here, this is an example of an alkyl group. And this one here, same thing, propyl, also an alkyl group. And how does it come together? This molecule right here would be called 1. In fact, just make sure you put it in alphabetical order, and B goes before P. So 1-butyl, 4-propylbenzene. Let's see if we are correct. I don't want isobutyl because that's a little bit of a different one. 1-butyl, 4. Yep, there we go. Has the longer part on top and then the shorter part at the bottom, but exactly 1-butyl, 4-propylbenzene. But that right there is just an example and breakdowns of how these alkyl groups work. Make sure that you don't forget about the YL at the end. That is the key part about this. So I'm gonna write it down here, just emphasize. Replace ANE with YL. So if anything, this is the most important thing you should be taken out of this when you're working with alkyl groups. Okay, so let's see what they say here. Okay, and they do have the general formula there. That one, it's always good to kind of base it off the carbons you have. You want to make sure that you don't want to make any assumptions. So this formula here does work for most cases. In fact, if we look at the examples I gave you, you will see that exactly that's how we got the C3H7, because we have 3 carbons and then 3 times 2 is 6 plus 1. And then you can guess that exactly this one would be C4H9 instead of 10, because butane is actually C4H10. So you're kind of like taking away a hydrogen and replacing that hydrogen with the main group. And then that becomes the side group, aka the alkyl group in this case. So with that, this is also correct. Now let's move on to question 3. What is density? So the way I like to see density, personally for me, it's kind of like the amount of mass in a given area, if that makes sense. So density, okay, what is that? I see it as like the distribution of mass over a certain area. And yes, they do have a formula there, you know, the density sign. It looks like a P, kind of like that, is equal to mass over volume, okay? This is volume, this is mass. This is the formula right here for density. But that doesn't really conceptualize it, does it? You just give a formula, you kind of have to visualize it. So if we're going to make some examples here, think of, I guess, suitcases, right? You know, like when you fill it up, usually like, and you lift it up there, so you have a whole suitcase bag, and then there's stuff in it. All right, you can say the whole thing is like 50 kilograms. That's the mass. But you could also say that this area here has a greater density than this area here. This density here would be less. Why? Because the stuff's near the bottom. Exactly. So if I kind of like took the volume of this area here and divided the mass by that volume, I'd get a higher number than if I just divided by the whole volume, because you kind of have to, it's kind of how the mass distributes itself. A better example of density would be, for example, if you had two things that weighed the same. Let's say this is like 50 kilograms, but this thing also weighed 50 kilograms. Imagine if, like, exactly like you are, aluminum foil actually is a perfect example, actually, because remember how if you, so let's say you had a whole giant sheet of aluminum, really heavy sheet, I guess, because it weighs 50 kilograms, but then you were able to compress it all the way down to this rock solid aluminum ball. Same mass, but this is way denser, and you'll feel it too. As in this, you know, those 50 kilograms, you could probably like punch through it if you tried hard enough. You could pop a hole in this thing, bam. But this, there's no way you're gonna get through that aluminum because it's so tightly packed with each other. So that's how I visualize density there. If they ever ask you to explain it, just remember that the volume plays a key role. So two things can definitely weigh the same thing, but one can be denser than the other based on like how much volume there is. Another example is like people in general, actually. You've seen like tall people, and they would weigh the same as like a shorter, stockier person, for example, but they would have the same weight. Let's say like this is like 70 kg, both of them. This person is more dense. You'd probably assume that if these two weigh the same, the shorter one would probably maybe have more muscle mass or fat or something, just because there's like more, it's kind of like he's more knit up in a certain area. Just be careful though, because you have to make sure that you are calculating the volume right, because for example, if it was like a tall skinny person and like a short much stockier person, they could actually end up having the same volume, so they'll be around the same density. So if you ever want to think about density, I would always kind of just refer to the aluminum example, because that one you can really conceptualize, and you can grab any paper, crunch it up, and you'll see that it's more dense, and you'll feel it based on the paper that's completely laid out flat. Okay, so this is correct because they have the right formula, mass over volume. And now let's move on to question 4. How do you convert 45 degrees Celsius to Fahrenheit? Now this is another example of make sure you keep your units. So what we have now is 45 degrees Celsius, and what we want is Fahrenheit. Okay, so how do we do that? Well, we start with the 45 degrees, okay, and of Celsius, sorry. And now we know there's some ratio of Celsius that can be converted to Fahrenheit and work from there. Now this one seems to be more like an equation, but let's just see here. So if we have temperature, Celsius is equal to 5/9 of Fahrenheit minus 32. Wow. So if we did, yeah, in this case, this will actually not work. You just actually have to use a formula. So if it's not a one-to-one conversion, you can't use this because Celsius has things you have to add to it. Same thing with the Fahrenheit. So with that, let's actually get our formula. Degrees Fahrenheit is equal to degrees Celsius times 9/5 plus 32. Now, the thing is that because for some classes they really do focus on like temperature changes and stuff, they do expect you to memorize this formula. So I would go ahead and write it down somewhere because it can come up quite a bit, and it would be unfortunate to miss out on marks because of not knowing this formula. So let's see here when we plug in our numbers. So 45 degrees Celsius times 9/5 plus 32. So 45 degrees Celsius is equal to 113 degrees Fahrenheit. And think about that, that does make a good amount of sense because this is a really hot day. Like really, you don't want to go outside actually. And for my time actually living in the States, I would also know that this right here, this is like almost fever type of, like way beyond fever temperature. Like this is not something you want. So these two do correlate. It makes sense in my head. Let's see if we got it right. They explain how Fahrenheit and Celsius came to be. Very interesting. And they ended in 113K. So it is correct, but just be careful because K means Kelvin, and we're not doing that. Okay. The formula to get from Celsius to Kelvin, which is something that you will most likely need in chemistry, is that 0 degrees Celsius is equal to 273.15 Kelvin. That's just a conversion. So then you have to keep now, and it's 1-to-1, as in if you add 1 here, you're adding 1 there. It's very strange in that sense, as in, because 0 Kelvin is not, it's only a hypothetical at this point. It's not a real thing. That's literally where supposedly you have absolute zero, where particles stop moving completely. So I guess 273.15 is like their benchmark of the freezing temperature for water. Strange, but just fun, interesting fact. Point being that they do have the right answer, but I'm going to remind them that it should be in Fahrenheit, not Kelvin. Fahrenheit's always a tricky word to spell. Yeah, I would not expect that. So, with that, this is correct. Let's move on to question 5. What are structural isomers? So, structural isomers. Let's see what we have here in terms of information. Oh, structural isomers are just things that have the same molecular formula, but just different structure. So it's kind of in its name. So structural isomers. Okay, so like I said, same molecular formula, different structure. Now this is just one type of isomers. There's also things called constitutional isomers, which are even like similar structure, but they're kind of like twisted in different ways. But we're focused on structural isomers today. And the way that works actually is that, so let's see here. Let's say if I give you C4H10. This right here is also known as butane. But I could draw it like this, okay? Or I could draw it like this. Yep, those are really the only two I could draw this. And you notice actually that if you count the hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So both of these are still C4H10, but this one here is called isobutane. That's just the name if I remember correctly. Yep, that is it. Very pops up a lot in chemistry, which is why I just remembered off the top of my head. But exactly, these are what structural isomers look like. And it's important that you note this because you maybe ask questions like this where it's like, which of these are structural isomers? So with that, that is in a sense what they are. Just make sure that you're counting your properties correctly. You don't want to miss a hydrogen or a carbon or any other element that might show up and assume that it's not a structural isomer. And make sure they match exactly the same. Like for every carbon one has, that one has to have the same amount of carbon, and that applies to every other element there as well. So let's see what they have. So chain isomers, which is kind of like what we did here. You see they actually use the butane and isobutane. They have functional group isomers, where interesting enough, they have first an alcohol, and then, actually that's not alcohol, sorry. This is an ether, I believe that's what it's called. Let's review that. And then they have propanone. That is not an ether, that is oh wait, no, not even an ether. Both of them are ethers. They're acetones and ketones and acetones, I believe, because ketones are the ones where the oxygen's in the middle, and then the other one is where the oxygen's at the end. But point being is this is another example of a structural isomer. See how they look different, but if you count it, they have the same exact amount of elements for each type. And the last one to talk about, position isomers, is just when you move like any halogen or type of structure around the chain. The point being is that they still have the same exact amount of everything else. So that is what structural isomers are. Just to recap, same molecular formula but different structure. If it's easiest, think of the butane example where you just move the bond. In fact, I could even show that. You move this bond and you put it down here, and bam, that's butane versus isobutane. So with that, question 6. How do you determine bond angles of a molecule? So this one can be a little bit tricky. Bond angles depend on two things: the amount of bonds it has. So bond angle, it depends on amount of bonds and amount of lone pairs. So we're actually going to create a table here. We're going to break down each one, but I want to make sure I have enough space, so let me just write it like this. So amount of bonds, you always have to start with a minimum of 2 bonds. So let me just put bonds here: 2, 3, 4, 5, 6, and yes, things do expand that much. And now, amount of lone pairs. In fact, let me just move this down, so that way up here I can put lone pairs. That's 2, 3, 4, 6, 0, 1. In fact, might need more space than that. 0, 1, 2, 3, 4. I believe that's how far it goes for lone pairs. So let's start with, if it was something that had 2 bonds and 0 lone pairs, it would look like this. The element X, for example, just like that. It's called linear. An example of something like this, okay, would be like CaF2, okay, because calcium only has 2 electrons for it to give, and this is linear, and this angle is 180 degrees. Okay, so that is the first one. Now, with this though, if it had 1 lone pair with, I guess we can't really call it bonds. Think of it more of like the steric number, or things that is attached to. So not bonds. Let's just call them attachments for now. Something that's a little bit easier. Attachments. The reason why I'm saying it like that is because once you have 1 lone pair, for example, it'll kind of look like this, and this doesn't really have a, degree, because it's only one thing sticking out of it. That's like HF, for example, hydrogen fluoride. In fact, that's not even a good example, because that one has a lot more. What would be a good example for this? Maybe like look at the periodic table. No, that wouldn't even work either, because most elements, if not all, like to be a certain way. So let's just actually cross this out. And this just wouldn't make sense either. So these ones don't exist. So let's move on to the third one then. So now we have 3 bonds, and it looks like this. Okay, and this, the angle is 120, and this right here would be like a BH3 or BF3. Actually, I've seen that one more. Boron with 3 fluorides attached to it, and the reason why boron is because boron has exactly 3 electrons it can attach, and fluoride just takes up those spaces. So with that, that's would be what it looks like. Now if we had 1 lone pair in this, it looks more like this. Okay, and this would actually be like would it be nitrogen? I'm trying to think here, because these ones, no, it would be nitrogen. It might have been like, most things would not even bond like this. I can't think off my head an example like that, but this angle here would be like less than 120. That's really all we can infer from that. And then, you know, you can't do more than that anymore. But the trend is usually that once you start including lone pairs, whatever the non-lone pairs is, you just know that it's something less. There's no specified number, just because it does vary, but just know that once you start adding lone pairs, because electrons like to exert a little bit more force in the whole shell, things kind of get pushed and get squeezed together if you're not an electron. So with that, let's move on to number 4. If you had 4 of them, this is what it would look like. Sorry. you kind of have to draw like this, because it kind of forms like a little tetrahedral. But this angle is 109 degrees. Okay, that's what 4 would look like. And a perfect example of this one, CH4. That's what that forms. Now with the lone pairs, if we had that, this would be what it would look like. X 2 3, and actually we do have an example of this one finally. This would be like NH3, okay, because it has 5 electrons, so 3 of them can be paired, so that's 2 lone pairs. And this one, following the same rule, would be just a little bit less than 109 degrees, okay. And then now if we had 2 of them, oops, there we go, like that, this one is way, yep, I'm using the less sign, good, less than 109. We don't really know what it is. We assume that it's a lot less than 109. And actually a common example of this would actually be H2O. This is a perfect example of that, because oxygen has, 6 electrons, so it shares 2 of them with 2 hydrogens, and then the other 4 form 2 lone pairs. So that's how we get that. Okay, and actually note that the most common, I guess, attachments that most elements have is 4. It usually doesn't like to go past that, which is why I couldn't come with an example of that lone pair here, like this one. This one is very rare in the natural world, as in I can't even think of anything that would bond like that willingly. So if there was 5 actually, so this one looks kind of like this, where you have that, and then you have the 3 chains kind of like circling this, forming a circle with each other like that. Okay, so then this right here would be a 90 degree, and these will be treated like the 120 degrees up there, and that's what we have there. As an example for this, let me just actually get rid of that. I don't like that. The X is better now. An example for this, something 5, honestly could not tell you, unfortunately, because exactly 4 is the most common one, but that would be the angles for it. And then if you added 1, you'd still have this, and you still have kind of like the ring there, okay, but the bottom would be where the electrons go. Now following that, this right here, this angle would be less than 90 degrees, and this angle would be less than 120. You see how the electrons just keep forcing things to be close to each other? That was what would happen there. And now with that, oh no, sorry, I drew this wrong. This is actually the most stable form. This would actually be more like this, so we'll still have these, and then these ones will be pushed aside. So exactly, so this angle here, this is the one that's less than 90 degrees, and the angles between each other here, that's usually supposed to be 120, will be less than 120 degrees. So that's what would happen there. And once again, I cannot think of an example. And then it just kind of keeps going. So then now if we have 2, it will form an actual like a T shape actually. It'll look like that. Okay. And these will surprisingly still be less than 90 degrees. So not exactly 90, just a little less than 90 degrees. And then after that, we have a pseudo linear again, surprisingly, because now this, and this is like one of the few examples, the rare ones, where actually it is 180 degrees. The electrons have now pushed both bonds to as far as they could away from each other, which is why we get back to that balanced 180. So that's what we get there. That's it for that one. Okay, so now we can talk about the last row, the sixth one. So this one is the one that's the most full, and I can actually think of an example. It would look like this. So everything is 90 degrees from each other. So in any angle, even here, down here, they're all 90 degrees from each other. That's as far as they can be comfortable. And I believe an example would be like something with sulfur. Sulfur can do the, or is it phosphorus? Something with, and maybe phosphorus can actually do the 5, and sulfur can do the 6. Strange stuff. But one of those, something. In fact, I'll write it here, I guess, for you to search up as well. Because right now we're focused on just angles. Something phosphorus, something sulfur. That's what I'm thinking here. And then we kind of, so this is where I made the mistake earlier. So this is the one where the the last electron would be under it, so like that. It'll kind of form like a star, but because the electron is pushing everything up, all these are going to be less than 9 degrees. Okay, and now if we had it, 2 of them, it'll kind of form a sandwich. So because it forms a sandwich, it kind of follows the same thing, to where instead of it being less than 9 degrees, the electrons have pushed everything as far away as possible, kind of like what happened here actually. So these ones are all actually back to being 90 degrees away from each other. And then if we have 3 of them, we're back to a pseudo bent shape. 2, 3, and then this sticks out. But this exactly is less than 90 degrees. Okay, these ones you don't really have to worry about them too much, and we're going to actually draw the last one. So the last one is also something that looks quote unquote linear. So it's kind of like this one again, where the electrons have pushed the bonds as far away from each other as possible, and is back to being 180 degrees. So these 3 here are the only examples, are the examples I can think of where you won't have to put that it's less than what it's supposed to be. Everything else, once you go past 0, in terms of once you go past 0 valence electrons, 0 lone pairs, then the angles start getting tighter and tighter and start squeezing together. So with that and everything said, this right here is how you determine bond angle. It's based on the amount of attachments they have, what amount of bonds they have. And it goes from 180 to 120, 109, and then 90. Okay? Because that is the best shape it can put itself to comfortably fit all elements, or I mean all molecules. So now, number 7. Let's see. Yep. Bends. So they actually give us a name for this one. I guess for number 6, they tell us that, for example, what we just did with the oxygen here, this less than 109 is called a bent, I guess, molecular geometry. These are some of the things you may have to memorize along with their actual angle. So just keep that in mind, and I'm just going to let you can pause it here if you want to write all these down. Okay. Oops. Oh no. Okay. Now let's move on to the next question. So let's see here. What is the molar mass of sulfuric acid? Thank gosh that they just gave us the actual name of it. So H2SO4. How do we find molar mass? So to find molar mass, we need the periodic table, and we need to list out every element in sulfuric acid and then add the molar mass based on the periodic table of each element, and then multiply that by how many of them there are. So if I would break this down, H2SO4 has H, S, and O. But as you see here, with the subscripts, it has 2H, 4O. So now we have this, we multiply that by each molar mass on the periodic table. So we have, let's start with H, 1.008. Sulfur is 32.06, and oxygen 15.999. It's important that you do refer to your own periodic table because the numbers could vary, and you want to make sure you're using the ones that your class is offering, because that way you don't lose marks for being slightly off. So with that, 0 times 2, 2.016, okay, 32.06, and now 15.999 times 4, 63.996. And then now that we have all the constituents, we add them together to get the total, and that will be its molar mass. So we add them and we get 98.072 is the molar mass. And the way we write that, we put 98.072 grams per mole of H2SO4. So you see what I did here? I laid out all the constituents, made sure that I included the subscripts and any prefix that might be there. So if there's like 2 H2SO4 or something weird, we just have to make sure we account for each element in there. Then I multiplied that by each individual molar mass, and then I added it all together, and that's how we got to this answer. Okay, let's see. Yep, 15.99 times 4, and they get 98.07. Ooh, you see, their hydrogen was different from ours, and same with their sulfur, which is why it's important that you just go with whatever's in your periodic table. But this is still correct because that is what you're supposed to get. So, because they still have the 98.08, which is really like less than 0.1 away from mine. So, not going to try to check what numbers they use, just because, as you notice, some periodic tables do vary on the numbers, just because it is quite hard to quantify them and get an absolute number for each one, since everything typically is based off carbon, and some things may change here and there based on how many significant digits you're going towards. So, number 8. How do you determine steric numbers? So, funny enough, actually, I don't know if you caught on what I said earlier, but when I was doing this question here, number 6, right, I said attachments, but this is actually what's known as the steric number. Okay, this right here, see 2, 3, 4, 5, 6. Steric number is, okay, I'm gonna write this slowly so we can really get my handwriting, hopefully, is the number of bonds and lone pairs attached to the central atom. Okay, so this right here is what a steric number is. So now how do we actually apply this? So say I gave you an element and it looks like this. Okay, what is its steric number? All right, so the way you find that out, actually, you just count, starting with the bonds. So we have 1, 2, 3. Sorry about that, I don't like the way that bond looks. So we have 1, 2, 3, and then we add the electrons, the lone pairs. So it has to be lone pairs, so you don't count individual electrons, you count the whole thing of a pair. 1, 2. So this right here, this element would have a steric number of 5. Okay, now let's think of practical examples. If I gave you H2O water, what would the steric number be? We use the same concept here. Circle in each I'm blanking on the word. You circle in each bond, then you add the lone pairs. This has a steric number of 4. Okay, and as it does mention here, it is used in Vesper theory, and it's used to exactly determine molecular geometry, which is actually what we're doing here this whole time. Based on the steric number, we could figure out its angle. So hopefully that even clarifies the previous question here. And what makes this even cooler is that, as you notice when I mentioned sulfur, things like sulfur, phosphorus, those are the ones that break the typical steric numbers. Most things like to be around 4, as you see with oxygen. Even, for example, nitrogen is another good example where you think it's different, but when you count it again, you have 1, 2, 3 bonds, 1 lone pair, 4 at the steric number. So most things prefer 4. There are a few examples, I guess, other cases. Those will include like phosphorus and sulfur, and then hydrogen only has really 1 bond, so it doesn't. I'm pretty sure it doesn't have a steric number. If you can technically, you can say 1. It has a steric number of 1, but yeah, that's what you do there. But yeah, count the number of bonds, okay, and then count the number of lone pairs, add them together. That is your steric number, okay. And if you notice that you're not getting 4 for like most things, you just be wary, because that should be typically what you should be erring towards, unless the whole worksheet is just about like really rare cases. Okay, this is correct. So now, question 9. What is a buffer solution? So, buffer solutions, if I can try a different color, resist changes in pH. Okay, how? Because a buffer solution has a mixture of its acid and conjugate base. So the way this breaks down here is that if you added more acid, the conjugate base in it would resist that change until there was no more conjugate base left, and then it's no longer a buffer. Same thing, if you added a base, the acid would keep it around that pH until there was no more acid left, and then it would no longer be a buffer solution. In fact, based on what I described, actually, you should be familiar with these, the titration curves. Actually, when you're trying to titrate a weak base with a strong acid, or vice versa, a strong base, you're trying to titrate a weak acid with a strong base. But these curves typically look like that. Okay, so right here, this is where the buffering I guess ends, if you think about it, because here's like where the buffering is really taking work. You see how the pH is trying to increase, but as you're adding base, it's resisting it until we get to the point where there's no more of the, I guess, acid, and then all that's left is a conjugate base, and then you notice it skyrockets, breaks out of that buffer. So this is what it's looking like in terms of like the titration curve. But what you have to remember is that the buffer solutions only work, okay, this is an important part, with weak acids or bases. Now you're probably wondering why that's the case. So the issue with strong acids is that they dissociate completely, and strong bases. So let's say I put in HCl in a solution. Every part of it will separate to H and Cl. That's guaranteed. Now, if I put in NaOH, same thing would happen, where it just breaks down to sodium and OH minus. So the reason why this is important is because this right here doesn't really count as an acid and its conjugate base. It's just a complete dissociation of it. So that's what would happen there. But if we had something like CH, this is a different color actually, CH3COOH, this right here is also known as acetic acid. Okay, this would not thoroughly, because it's a weak acid, so does not completely dissociate, but there will be CH3COO minus and H plus. Now, the reason why this is different is because in the HCl situation, right, it dissociates completely. There's now no quote-unquote balance of HCl in the solution. It's all just H plus, which just goes 1-to-1 ratio. You know, you add some base, it reacts with the hydrogen, and you see that with strong base and strong acid, it'll look like that, a straight line, because it's directly related. The amount of base you add will cancel the amount of acid that I have, and it'll just be a linear relationship. But with this, because you have some of acetic acid and its conjugate base floating around in the same solution, that is when you have a buffer solution. And it's important to develop a strong buffer solution that you add some amounts of both the acid and the conjugate base. You don't just put the acid and then think it will dissociate to form the conjugate base. So with all that being said, a buffer solution, just to recap, it's never this change in pH. Okay, it only works with weak acids or weak bases. Okay, and you need, well, actually let me write it here, the last part, you need conjugate. Okay, if you just poured in acetic acid, technically that would be a buffer solution because it does produce some of its conjugate base, but it would not be a very good buffer solution because there would be quite little of its conjugate base. You would need acetic acid in one, and then actually CH3COO minus in another, and mix together to get a more of a proper buffer solution. So let's see here what they say. Buffer solution is a solution that can resist drastic changes in pH upon the addition of acidic or basic components. So let's see. Just gotta drink some water. Should contain a weak conjugate acid base pair, which means that it has to be its weak acid and its conjugate base. Yep. Acetic acid, they do mention that. Actually, that is a good point. The way they added the conjugate base is that you won't really see just CH3COO minus like on the label. It needs to be actually paired with something, and usually just pair with a salt. So this is its conjugate base because it's sodium with the CH3COO. And you know, with sodium, usually things just dissociate, and you just get the sodium plus, and then bam, your conjugate base is free to roam around. CH3COO minus. So that is what's happening there. Ammonia is actually another example. It's a weak base, and then you can add interesting ammonium hydroxide. I would think that that one would, I'd actually go probably maybe like NH4 Cl maybe, but that would just be me. But point being is that exactly, just make sure that you have the acid and its conjugate base, or vice versa, to form a buffer solution. It cannot be a strong acid or a strong base, or else it dissociates completely, and that doesn't work. It becomes a 1-to-1 ratio. And the point of the buffer solution is that it resists changes in pH. This is correct. All right, and now for the final question for the evening, at least. Okay, what is the molar mass of nitrogen gas? Okay, so what exactly is, in fact, let me just write it down first. What is, I don't want to go to periodic table. You probably saw the answer, especially if you can pause it. But for those that didn't see the answer, just want to work through this question. The molar mass of nitrogen gas. Okay, so what are gases? Gases typically, especially when you have an elemental gas, you will not find this roaming around in the air as an element. Another perfect example is oxygen. Okay, oxygen, I'm sure you've heard this. For the oxygen gas, it's O2. So you actually see for a lot of these gases that just float around, whether it's hydrogen, oxygen, or nitrogen, there's a 2 attached to it. Okay, these are its natural state for gases, and there's many more I could go through, but most of the time you will see it like that in nature. Now, with that being said, though, they're asking for the molar mass of nitrogen gas. If you remember what we did with the previous question, okay, we list our constituents, and then we add the subscript to know how much we're multiplying by, and then the molar mass of the individual element. So nitrogen gas, okay, we have nitrogen, good, 2 of them, and then 14.007. Okay, so now let's see here, times 2, that is equal to 28.014. So now to write this, we have 28.014 grams per mole of nitrogen gas. This right here is going to be your answer for that. Now the trick to these questions, as I mentioned, is that it may have looked simple to be able to solve it, but you have to recognize, and I do emphasize that you do try to memorize these natural gases that occur in the atmosphere, because you want to be able to make sure that whenever they say gas, that you balance out the equation correctly, and it's not just a single nitrogen or a single oxygen or a single hydrogen. It's come in pairs. Most gases come in pairs. Okay, and with that, let's see what they did. Yep, 28.02. They just had probably different numbers. Yep, 14.01 is what they used, and exactly got 28.02. So this is correct. Okay, so with that, I just want to thank you again for joining me this evening. I hope you have, for those that do have holidays around this time, enjoy your holidays. Other than that, though, have a good night. Make sure to check the links in the description below if you have any other questions. And thanks for tuning in, okay? All right. Bye.